Okay, Hangout is online. These are the two photos that we're going to be using to redesign or design from scratch the FRC-67 robot from 2014. Hotbot. Hot always has really, really nice designs. We're going to, in one sitting, do our best to get as much of the design out of the way as possible, figuring out all the constraints and the general sizes of things, and then getting started on a 3D model. So this model here, the robot functions by having this one large arm, picks the ball up by tilting down on this direction, scoops it up with the intake rollers and against this bottom bar here, and then the entire arm will rotate around, and there's a puncher, very mean looking puncher back here, powered by constant force springs, the same springs that are inside your tape measure. And that releases all of a sudden, firing the ball, punching the ball, and firing it out. Very, very powerful. Was a very successful robot. It was great looking too. Another cool feature is to center the ball. It had these, see the flames here, that's actually a four-bar linkage that'll come over here and slap the ball on either side to center the ball on the puncher. You can see here, this is the puncher when it's deployed. Springs are released. It's this large square here that'll hit the ball on all these sides here, and it's great. It'll fire it. Fantastic looking robot. Worked very well. Great on the field. So let's go ahead and get started designing it. So in SolidWorks, we're going to make a new part file. I'm going to move as fast as I can, at least with my slow laptop, and we're just going to get this thing done. So what we're always going to start with is, since we don't know anything about the profile or the design, the relative sizes of things, I'm starting a sketch on the right-hand plane. We do know some things. We know that there is a ground that the robot is going to be zooming across on. We also know that there's going to be a height limit that the robot cannot go above. We also know that the robot cannot extend over a certain width. It has to fit within this box when the match begins, and when the match has begun, it cannot extend beyond a certain wider width. And this is looking at the side of our robot. So that's what this represents. Origin down here is on the ground. We are going to create a rectangle. I'm just going to go back. We're going to finish finding what these sizes are. Great. So the height that the robot can never exceed is 60 inches. Goodness. My SolidWorks just kind of exploded for just a second. There we go. I undid my smart dimension. Gave me some sort of odd error saying that it was overdefined. That's better. 60 inches. Make sure that it's happy with that. Changing this value would result in invalid geometry. Previous state has been restored. I'm thinking that probably is because I'm going to give this a shot going right to the origin. I have no idea why this is happening. Goodness gracious. Try 60 one more time. Not going too well. So here's the next plan. Clearly this isn't working too well. Let's get rid of that horizontal relation so that way that line can pivot. Maybe that's what's causing the issue. 60 inches. Dang. It's obnoxious. Maybe there's something up with that line that I drew. SolidWorks is having some sort of issue. So draw a fresh line. Call that 60 inches. Valid. Static. All right, we're going to start over. Oh goodness, SolidWorks, sometimes you drive me nuts. So pretend this is our upper limit. Double clicking, by the way, lets you exit the line that you're drawing while still keeping in the line tool. So you draw one, well, before you draw next, you just double click and it'll not add the one that you're about to draw. Great, now let's try. Come on. Inches. There we go, that worked. So that's 60 inches now. Just because I like the infinite lines, I'm going to make all these infinite length. Hopefully it won't give us any grief about that. Now the entire width of the robot, this is going to be representing the width of the robot, but the protrusion is at a set number, and I don't remember what that number is, so let's go figure that out. You're going to find that number in the game manual. So for instance, this is going to be Game Manual FRC 2014. And look at that, first has great documentation. Let's see here. Is this really 2014? Sure is. But you have to go to the archive. That was the old website they had set up. So here we go. This is it. Admin manual, one-page game description, game animation. This I must have clicked incorrectly. Trying one more time. Those were the admin manuals. Try one more thing. All right. Thank you, Team 2051. They uploaded one directly to the internet. So there's the 2014 field and the trust and all the other things. But we're going to specifically be looking at frame perimeter rules. So there are 32 matches for frame perimeter. We're just going to cycle through. A robot's horizontal dimensions may never exceed 20 inches beyond its frame perimeter. So there's your robot, there's your frame perimeter. Anything that is going to ever protrude out of there has to be less than 20 inches. So that's the number that we are looking for. So I thought it was 15 in my brain before, but it turns out it's 20. Very good. Just because this is going to be symmetrical, I'm just going to mirror this to the other side instead of doing an entire other thing. So there's the mirror line, and those are our two details. Come on, get out of the way. Fantastic. There's that, and just so I can make it nicer, makes it a little bit cleaner like that. So this represents the bounding box that every robot has to fit in. We don't know how wide the robot is. When we come back over here, we can see it can be any width. We get to choose what it is. However, there is another frame perimeter rule that should be, I don't know where it is, but Total length of the frame perimeter must not exceed 112 inches. That is this fantastic rule that we're going to need to know. So the sum of all the sides here, as if you're wrapping a piece of string around it, has to be less than 112. So we're going to leave this be. We're going to take a look at the robot from the top-down view. This is on the right-hand view. So that's a good sketch, but our robot's going to be three-dimensional. So let's take a look on the top plane. The robot is going to be centered on the origin. I'm just going to grab that, pop a thing on there in the origin. For instance, I have no idea what dimensions this is going to be. So we're just going to place it empty for right now and put some arbitrary dimension over here. And then we do know that the frame perimeter is going to be 112 when we start. So you can create an equation, 112 divided by 2 minus the other dimension is going to give you, the other dimension minus. You got to make sure that it's not negative. So we're just going to put the invert the thing. There we go. So now if you take the frame perimeter, no matter what, since we set that equation up, no matter what, your frame perimeter total length is going to be, well, that's 200. I must have done that wrong. 1 second. Minus parentheses. Don't forget your parentheses. Just joking. That didn't affect anything at all. Total length. Well, that's incorrect. I must have forgotten how to math. Well, that's odd. Because if we take, let's say this is 30 and 26, the sum of the parts going all the way around is 112. Oh, it's very odd. I don't know what had happened there. Must have been some crazy thing I've done. Scratch that last. Well, we set that equation up correctly. So the equation truly is the other dimension minus 112 divided by 2, or whatever your frame perimeter is going to be divided by 2. That will solve your, from this side, solve this equation here. So if our robot was 30 inches, it would have to be 26 inches. But in FRC, we need to make sure that we play correctly by the rules. Technically, as long as your design is initially spec'd at 112, they can't nail you down on the rules, but it's always good not to run up against that line. So if you just subtract 1, if you just do a frame perimeter, design frame perimeter of 111, that would be ideal. So just do a frame perimeter of 111, divide by 2. Just to make your life easier once you get to competition and you're being inspected and everything, just to make sure that you don't accidentally go over your frame perimeter. So in this case, it would be 30 by 25.5. Perfectly awesome. So we now have 2 dimensions of our robot laid out. But let's make these two sketches talk to each other, because currently we've got the right view and we've got the top view. We'll be adding a front view later. Let's make everything dependent on the top view. So I'm going to time travel, put the top view at the top of the time travel tree, which means when I edit the right-hand view, I'll be able to see the top, and I can add relations to it. If you can't move your top plane to the top in this order, it means that it's referencing the right plane. You just have to delete that reference. But in this case, we're going to make these two things pierce. When we pierce those two, you can see it's essentially coincident, this line. That means that this is going to be constantly relating to whatever's underneath it. So if we go back to our top view and we say this is just joking, this is going to be 40 stuff, you'll see that this sketch updates. It's still coincident with that pierce. So let's take only data that we really have any idea about is just the aspect ratio of this robot. So who knows how big this robot actually is. If we look at it with the 24-inch ball, it might be 24 inches in diameter or a little bit bigger than 24 inches in diameter. That's the size of the ball. So what if it was 26 inches wide? So let's jump in. Let's make this 26 inches wide. Actually, it wants to be the other direction. So we can see here that it's supposed to be 29.5 inches long. So I'm just going to do 29.5. Gets it in the right orientation. That way, this is the width. We're looking at the side profile of the robot, which is going to be longer. Great. So does that look about right for aspect ratio? I think it might be a little bit boxy. So if we can make this a little bit longer, maybe it's supposed to be, I don't know, 30.5. Maybe 31.5. Maybe it's exactly 24 inches. We can see here that's about the right aspect ratio. So that's about the ratio that they had. It was probably 24 inches frame perimeter wise. There is another variable that we kind of forgot about, which is the bumper. So if we go into our top-down sketch, this is the frame perimeter. That's what this represents. But there's also the bumper perimeter. If we take our offset entities tool, bumpers are 2.5 inches, but the back plate for the bumper, the 3/4 inch plywood, that's 3/4 of an inch. So we can add those two numbers together. What do you know? That is our bumper perimeter. Very good. So that gives us a sense, again, of where it is. Just a note, though, this dimension here is exactly to the frame perimeter. When we looked up that rule, it had to be 20 inches from the frame perimeter. It doesn't matter where your bumpers are. In this case, the bumpers are going all the way around. If we wanted to, we could have the bumpers split, but as you can see here, bumpers go all the way around. In fact, they made their bumper one piece, and it went on just like a sock. But when I saw them at competition, I had kind of fearing for the robot. They were whacking this bumper down with hammers, and they had to whack on the red bumpers and whack off the blue bumpers and everything. It was quite horrific to see that sight on such a nice, elegant robot. Their bumper system didn't work too well. So I would recommend splitting up your bumpers into 4 pieces. For instance, if you look at your robot here, you might extend this entity over here and that entity over there. Break up your bumpers into multiple segments. So that way you have one bumper here that's longer, a narrower bumper, a long bumper, and a narrower bumper. You could split it up in the other direction too. That's up to you, whatever fits the design more. Great. So now we have our bounding box. Our bounding box is the most important thing right now as we're starting off our design. We had to specify the top-down top-down view because we needed to know the width of our bounding box, how much we had to go for. But in reality, when we'd be starting off this robot design, everything is dependent on another. So you would kind of start with, and who knows how long of a line this might be. You might not know that it's going to be 31.5 inches in the end, so you might start with 30 inches and then realize, oh, I can't package everything that I want to, so you'd make it a little bit longer, and hopefully your robot won't explode. So it's a lot of a give and take, but for the simplicity of this example, we're just going to say that this is about right. We might have to go back and change that number later on. So here's our bounding box. We have our robot that is going to be fitting what at the beginning of the match has to fit inside this area here. But what does it have to play with? Well, it has to play with spheres that are 24 inches in diameter. That's a little bit big considering how big a robot can be. Yeah, that's a little bit scary. And you know, we can't even have our entire, you know, it's gonna be a challenge to get our robot to handle these large spheres, but we know that it can be done. We can see here this is a successful example. And what they did was they had this arm. So let's get started on designing the arm. But before we can design the arm, we need to know, well, what does the drivetrain look like? So we're going to design our drivetrain. Here we go. This is the side view of our drivetrain. We can see here that the design they chose to go with was a sheet metal drivetrain. Those are very nice, robust, light. However, on Rat-Pak, we've had trouble with them. We just spend so much time on the drivetrain, we end up losing our train of thought for later on getting the top hat done correctly. So I would recommend on Rat-Pak until we master the drivetrain and really figure out exactly what we want to be able to do. Use the Vex's West Coast drive. And West Coast products are fantastic. They are all part of a system and they all fit together masterfully well. This is a really simple example here where it's just this bearing block that'll jump right in to a piece of aluminum extrusion, and you can mount your wheels wherever you want. And it's already prefabricated. You can just add the pieces that you need here. But make sure that you buy these before the season starts because they go out of stock very quickly. So definitely use West Coast Drive this year until you master the drivetrain. So what can we see here? We can see a couple of details. Drivetrain's out of sheet metal. It is, let me zoom in. It's got one piece of sheet metal, two pieces of sheet metal, four pieces of sheet metal, and this fancy tube that comes and connects to it. We can also see here, if we go in a little bit farther, I'm going to assuming it's backwards. If we go in a little bit farther, we can see that there are pieces of sheet metal here as well. So there's actually a total of 6. There's inside sheet metal and outside sheet metal. That's going to be important for us to know. But for right now, we know that this is going to be here. Our robot is going to have wheels. So what wheels are we going to be using? It's very difficult to see what kind of wheels we've got going on here, isn't it? The other one isn't as much of a help either. However, Hot usually uses 8-wheel tank drive. So for this instance, how about we use 8-wheel tank drive? 1, 2, 3, 4. Yeah, I think that's probably what they used here too. You can see the where they put lightning holes. They skipped one over here. That's probably where they mounted one wheel. They skipped some here all in the center. This is probably for mounting the gearbox and other accessories. So this is probably 1 wheel, 2 wheel, 3 wheel, 4 wheel on each side. Makes 8 total. So that means that they packaged 8 wheels. Whoops, my bad. I accidentally added a tangent relation. So let's just add 2 wheels on the left side, and we'll mirror those over later. These wheels are going to be the same diameter, so make them equal. and they probably used just like good old hot 4-inch diameter wheels because there was no obstacles on this year's floor. It's very important when you're dealing with these tank drives that you set an offset between these wheels. I want to make sure that there's at least a 1/4 inch difference, that the center ones are lower or the outside ones are higher. We also need to make sure that there is space between the wheel and the wheel edge and the edge of the frame. So let's go ahead and just set that arbitrarily at 1 inch. We'll change that later, I'm sure. To reference the side of the wheel here, I just added a point. And when you add a point, you can see here that it gets these diamonds in the corners. When you hover on top of them, you can place points at those places, and then you can reference those points. So that's all happy, fun, and games. Then we need to mirror this over to the other side, and we'll see how to do that here with just the mirror tool. Entities to mirror. We're just going to keep mirroring this over to the other side here. Look at that. Very nice. There's one more thing that I want to do is figure out the spacing of this wheel. You can see here that we don't really know where it is left and right. Don't worry about up and down just yet. We'll get to up and down. I'm just going to place lines on these wheels. And you can see here that the line lengths change. It gets shorter. As this one gets shorter, that one gets longer. So just for an arbitrary thing to make it nice and simple, I made those lengths the same. So the distance between wheel centers the same. That's all good and fun. The next thing that we need to have is the distance from how far the wheels are protruding down. So I'm going to add another point to the bottom and reference it here to the bottom of the plate, and we'll just set that arbitrarily at 1 inch. As we're using such small wheels, we got to be careful because our bearings that we'd be using, well, it depends on how you're doing it. If you were going to set bearings inside your frame, you'd have to be careful because the bearings are 1 1/8. So you need to have at least this size big hole, which means that this material here might get some abuse. So you just got to make sure that that's okay. But we're likely just going to use actually 5/8 shaft, 0.625 shaft. So as long as there's this much room here on the plate, you'll be just fine. And the more critical thing is this one over here. That one's closer to the bottom. So we got to make sure that that 5/8 circle isn't running off the edge. And clearly it's not. We're completely fine. But if you had thought that this would be great as 1 5/8, look at how close this one gets, right? Your bearing or your wheel shaft is going to be really close to the edge. You got to make sure that, especially when it gets a little bit lower, that your shaft isn't overhanging on the edge there. So that's just something to consider. Make sure that you don't make that mistake. But hey, look at that. Now our robot has wheels. And just to make it pretty, let's just mirror this over to the other side. Having detail in these drawings is very important. It can remind you of things in the three-dimensional world. But how tall is clearly our wheels are going to be on the ground. So go ahead and make those tangent. And they should be fully defined right about now. If you haven't fully defined them, figure out how they move and then constrain those. Great. But how tall is our drivetrain? Well, that would be very nice if we could just make this super duper skinny like that. You very well could. You just have to make sure that you have to make sure that you can mount the bumpers. So let's worry about the bumpers right now. The bumpers are a very important part. Before we even start looking at the arm movement, we need to make sure that we understand where the bumpers are, because the bumpers are going to be the thing that are actually interfacing with the ball first, very likely. We're going to need to make sure that we design around the bumpers. So to do that, I'm just going to add an arc. Actually, just joking. I'm going to add a line. This is representing the thickness of the plywood, and that is 3/4 of an inch thick. And then I'm going to add an arc and another line and an arc and another line. Look at that. That's a bumper from the side profile view. That's all we really need to make this work. So we'll make these each one of these segments tangent to the next because it's going to be a very smooth wrapping action. When the one second, let me finish that up. Good. There is a plane here. That 3/4 inch is completely and totally wrong. Just joking. It's going to look more like this. There is a 3/4 inch plane. That represents the plywood. That's where the plywood is. So go ahead and make that 3/4 inch. The pool noodles are complete circles, and so they're going to be tangent with the back plane. So you can imagine here, I added that tangent relation. They can no longer move out as soon as I make these equal to each other. And I set their diameter as being 2.5 because that's the diameter of a pool noodle. There we go. Now they can no longer move out. You can see that this line here is black. This circle, you can see how it's completing here, and it gets tangent to this plywood piece there. So that's very good. That's one bumper. That's going to be on the left-hand side. This is going to be the same usually every year. Make sure you read up on the bumper rules in case anything's changed. Very good. So now we're just mirror this over to the other side because it's really nice when you see a whole robot come together. When mirroring, I like to have a dominant side and a non-dominant side. On the dominant side, in this case, looks like it's the left side. I'll put more construction geometry for defining things, like this vertical part of our bumper plywood. But when I mirror it over, I don't need that information. There is one more thing that we need to have, is the height of the bumpers is going to be 5 inches, or the two pool noodles are going to be stacked on top of each other, and they're going to be tangent. And you can see here, now the height or the length of this thing is 5 inches. You know, they're tangent to each other. It's all good. They get it. They're hanging out. So now we just need to define the height of our bumper up here, up and down. There is a rule that defines that. We need to make sure that we research that very well. So if we come over here and we search bumper, there are lots and lots and lots and lots and lots and lots. Bumper zone, that's what we're really looking at. So let's look at the bumper zone. There are only 6 mentions of bumper zones. Great. So bumpers must be located entirely within the bumper zone, which is between 2 and 10 inches from the floor. The reference to the robot floor, yeah, so just if the robot's on the floor, it has to be between 2 and 10 inches. So this is also what the bumper looks like from the side profile view. You've got each one of the pool noodles. They're tangent to each other, tangent to the backboard. And then you've got your cloth hanging over. That cloth is kind of negligible. Doesn't really affect too much. But if you have hard parts that might protrude, you know, like this 1/8 inch plate here, you might want to add that in because that adds a total of 1/4 inch to your entire robot width, which can be significant. So make sure you add that in too, if that's the design that you're going to use for. But 2 and 10 inches off the floor, that's the important number that we get from here. So let's jump over to SolidWorks. So that means that the upper bound, we could place our robot bumpers 10 inches from the floor. They could be this tall, or they could be as low as here to there, 2 inches off the floor from the bottom. So for right now, let's just leave that at 2 inches. Hot likes to put everything as low as possible and keep their CG low, especially when they have such a tall robot. And when we look at their robot here, see their bumpers are essentially flush to the top of their drivetrain. Protrude a little bit, but in our case, let's just make them flush. So now that our robot bumper height is defined, let's just take our height of our frame and make it match whatever the bumper is. Fantastic. The next thing that you probably get into for designing the drivetrain is figuring out the gearbox, and if the gearbox doesn't fit inside this height, currently this height is 5 3/4 inches. It should fit, but in the case that you can't package it, you're going to need to make that frame taller. But those are all things that you can give and take. So there's an abstract drivetrain. It's looking pretty good. Very nice, very nice. Now we've got this ball. There's the ball. Pretend our robot is driving up to it. It touches the ball right there with the bumper, and that's all happy. But how does this robot actually function? It's going to need to take the ball from the ground and store it up here, and then have something that fires it, pushes it out. So let's go ahead and get started on drawing whatever that is going to be, and that's going to be an arm. They integrated all of that functionality into one system. That's putting all of their eggs in one basket. They have quite a cool bit of detail here. We can see that they have some pneumatic cylinders on the bottom of their, these two bottom pegs each have their own pneumatic cylinder. Who knows what that's used for? We'll probably figure that out later on. I'm guessing that this is used for tilting these prongs down, so that way they can scoop the ball up more, but we'll take a look at the geometry and figure out if that's needed. And then they have pneumatic actuated 4-bar linkages that center it. And they've got this intake. So we can see how that all plays in together. So, and then they've got a pivot point that's back here, and a puncher, of course. So let's get the structure going for wherever our pivot point's going to be. Pretend that that right there, this point right there is our pivot point. We need to support that pivot point. It's going to need some structure that goes between it and whatever it's gonna, it's gonna need an axle, really, something to pivot on. You can see here that, let's see, is this better? Yeah, this is much better. We can see here that there is this structural brace that comes back here, and the actual pivot point is up here. They've got this, oh goodness, scrolling. This is a sprocket that controls the angle of the entire machine. So back to our SolidWorks CAD model. Instead of having a point here, let's make the pivot point a sprocket. To get the best gear down ratio, this is going to want to be a pretty big sprocket. So let's say we found an 8-inch sprocket, and that was pretty good. So there's our sprocket. This is signifying our pivot point. We need to support our sprocket somehow, and they had something, just I'm going to do a rough approximation. They had some bars that came from here, front side of the drivetrain, to meeting this shorter bar. And let me make sure I got that orientation right. Yep, that's right. I got that right. They likely made these two bars perpendicular to each other. That way they have the best force. You know, all the force that's being shocked back here is being applied perfectly linearly to this support bar. But we don't know that for sure. This perpendicular may have to go. It might have to be at a slightly odd angle in order to make it work. So there's that. We don't know where this pivot point is going to be located. We could lock it arbitrarily into space for now, but let's just entertain ourselves and let's keep building off of this undefined geometry. We're going to need a puncher. That's going to be a really critical point. And we're also going to need an intake roller and this scoop down here. So let's take a look at the scoop. If we were to scoop the ball directly, as if we slipped a spatula underneath it, we would need to grab the ball with an intake roller that's up here somewhere. Intake roller is going to be tangent to our ball here. And then that scoop would have to go on the ground. Let's pretend this line here is the scoop. It would need to ride on the ground in order to get underneath the ball, or give it something to for the roller to pinch the ball against. What Hot did was kind of interesting. Instead of holding the bottom of the ball, they're holding the edges of the ball. They have two of these pinch bars. And what that's doing is, they're not holding the ball from underneath. The ball is actually drooping underneath these two bars. So we're going to mimic that, but we need to know where on this circle is our ball need to be pinched at. Because if it's going to be, this is always difficult to explain, but if you can see, the ball is going to be drooping underneath these two pinch bars, which means that when you're looking at it from the side, that you're not going to be picking it up straight from the bottom. You're going to be picking it up somewhere here, somewhere closer to the center. But how close to the center is that? So to answer that question, let's make another ball that's over here. This isn't going to be part of the robot. This is just going to be a model that's over here in space. Pretend that this ball is, we're looking at it from the top. This ball's from the side, this ball's from the top. We have a couple of bars that are coming across it. These are the bars that are holding the ball. This is what the ball is essentially rolling on. Those two bars are equal to each other. That way, when you move them across, they are equally centered. The lengths are equal, which means that they're spaced equally on the center. Now this is kind of cool. This here, the length of this line, say we're going to make this, we don't want this to be driven here, just you'll see here in a second. I'm going to make this a driven dimension. And let's say that we are holding this, the two prongs were the 24-inch diameter ball, is 18 inches apart. So this is where the prongs were located. That means the length, the interference between the prong and the ball is going to be at, the prong is going to be 15.87 inches. We could imagine that as being the prong length, but this is also the cross-sectional diameter of the ball. If you kind of thought about this as the ball from the top-down view, and if you took a knife and sliced the ball perfectly right there, and you looked at this line from the side view, that would be a circle, right? This line is the diameter of this section of that circle. So you could essentially draw a side view of this same exact ball that had a point that was vertical from that point, as long as their center points were on top of each other. Now you're looking at the side profile of this ball. There's the rest of the ball. Imagine you sliced it at this line. This is what it's going to look like from the side profile. You're going to get this diameter circle, which is the same as the length of this line. Now, this diameter circle is really, really handy. I'm just going to fix this. That way it's fixed in space. The only time I think fixing is appropriate when it's just a model on the side. So here, this is our circle. This is essentially what we're trying to pick up. This is the effective diameter of our ball now. So while the ball might be this big from the side, from its silhouette, we're actually only interacting with this diameter, which means that whatever we're using to scoop, pretend like this is our scoop, we're not going to be trying to scoop this part of the ball, the outer silhouette. We're trying to scoop just the edge of the ball, right? If we scoop this, it's going to touch, as long as these two prongs are 18 inches away, it's going to touch the ball right there. Now say that our prongs were 9 inches apart, you can see that that intersection gets, that changes rather significantly. But if it's back at 18, we can see that's what we're going to be interacting with. So let's say that these prongs are indeed 18 inches apart. Who knows if that's exactly what they used, but again, we can change that number later on. And we're going to interact with that number. That's going to be very important. Whatever that number ends up being, that's going to be very important. So let's make these two circles equal. Now, the cool thing about what we've just done here is we're making our model parametric, which means that every single dimension that we are specifying is coming from just kind of like one place of logic. This diameter of this circle comes from the space between these two lines, the space between the prongs. So if we wanted to change those prongs, as we've shown that before, it's going to change the model. And as we add more relations to the model, the entire model is going to change to fulfill whatever this number is going to be. That gets to be like automating our model, and it gets to be super awesome and cool. Very good. So let's pretend we were going to make our ball hit our bumper. When the ball hits our bumper, and it's tangent right there, our roller is going to be in contact with the ball. Remember, the roller can never cross this line. This is the outer. This is as far as all of our hardware can go. The ball can cross the line, but the hardware cannot cross this line. We need to specify some compression bars. I'm going to call these compression bars. These bars here that we've just defined, these guys, those are going to be called compression bars because they're compressing the ball against the roller. So we're going to draw a couple compression bars. There's one, and this is what the ball is going to roll onto. All right. This is symbolizing, this bar here is essentially symbolizing what this is. That's what it looks like from the side. This is what it looks like from the top, essentially. So next thing is let's get some structure that ties those two things together. Now, I'm thinking through this the very first time, so I apologize for all the silence. There are two really important states. Now, let's just define some tentative geometry. For instance, there's the connecting pieces. These two things are perpendicular to each other. Who knows where this is actually placed, but that's at a midpoint to each other. And this is what the robot looked like. All right, there we go. Everything's perpendicular to each other now, which makes logical sense, right? How big is this diameter of the roller? That would be a really easy number to specify that would answer quite a few questions. This roller, I'd say that looks like 2 inches. I have no way of knowing, but let's say that we made this work with a 2-inch roller. Looks a little tiny just compared to everything else. Let's make it 3 inches. That makes it look cooler. All right. Now, a really important thing is going to be when we're picking up the ball, there is an invisible line between where the center point of our pinch point, or actually just joking, there's an invisible line between where the roller intersects with the ball, so right there, and where the compression bar intersects with the ball. So if you place a line at the intersection of those two things, for instance, this needs to be constant with both the ball and the roller, and I think I already nailed that as the point of intersection there. there's a really important thing that needs to happen for every single successful intake, is that you need to have a really good grip on the ball, or else it's going to roll in as far as it can, and then it's gonna fall out of your intake. If you're squeezing the ball like this, pretend like your intake roller was way back here, and you squeeze the ball here. See how this line is super far behind this center point of the ball? Now what would happen if you placed your intake roller over here? Looks like you've got a really solid grip on the ball. You know, it's being squeezed between your intake roller and your compression bar, and it's fully kind of encapsulated inside your robot. The sweet spot between a really good grip and a not so good grip is if the imaginary line between the intersection points here lines up exactly on this circle, the center point of the circle. In a perfect world, you'd nail it right there. You'd make these two things coincident with each other. So that way, it's always going to nail it. It's gonna squeeze the ball perfectly. And you can see here, this is figured out a way to. It's already kind of pseudo-defined our geometry. I think the reason for that is it shouldn't be defined all the way, except I added this accidental relation of defining the center point of the roller to the edge of our hardware limit. But there's also another really important thing, which is that hardware limit. Our hardware cannot pass this point. So even if you made this, let's make this tangent, and instead of making this 20 inches, let's give ourselves some room, 19.5 inches. So now when we make things tangent to this, we're actually safe. We've got a 1/2 inch of clearance. But now take a look at what happens to our robot design. This is defined in space. These are with all the constraints that we've very carefully added. This is the only successful solution. This is the only place that it can be, because the ball is defined to the bumper and the floor. This imaginary line's at the center point, and the roller here is at this diameter. The compression bar is at the location here, at just the right spot. So if you imagine, again, changing this, you can see how our model is going to change. In this particular instance, you can see here the compression bar is inside our bumper. That's going to be bad. The only way that we can get around that is to be putting a cutout in our frame and making sure that our bumper doesn't interfere with our robot. We can see here that we're really, really close, but we're actually too dangerously close, I would say, because right now all the geometry that we've ever drawn on this arm has been two-dimensional. You can see here this is only a line. If we used but all the aluminum that we'd actually be using has dimension to it, has a thickness. We need to add thickness to our robot. So for instance, let's just use offset entities to make this really fast. Say we wanted to use 2-inch stock, right? There we go. 2-inch stock is right there. 2-inch diameter tubes, who knows? Look at that. We are actually already interfering with this, with our drivetrain. So that means a couple of things. That means that our arm cannot, well, simply our arm can't be like this. Something has to give. We have to change something about our design. For instance, what if this wheel was not tangent to the edge of our frame? What if it was inboard more? You can see that only worsens the problem. As we move it out, it solves the problem. You know, our arm could be like this. It could be all great. But as we bring it back, it makes the problem worse. So in this particular instance of, this is a variable we could change, putting it as far out as possible, making this tangent is contributing greatest to resolving this issue. What other variables could be changed to make this issue go away? We have this variable over here. We could change how the spacing. For instance, what if this was not 18 inches, but 20 inches? You see here that means that we'd be grabbing the edge of the ball more. And look at that, we could actually almost cut it. There's a cool thing of how we're doing this. We could make this defining smart dimension over here. We can make that driven. And when we make that driven, you see that everything turns blue. And we can actually go backwards. We can have the model define these numbers. Say that we wanted to make this tangent to our bumper. We can do that. And there it is. And we actually have some more freedom of what number this is. Control Z that thing here. That is indeed tangent. There is something funky here that I wanted to fix. I just want to extend this entity out, because there we go. That's more of what I was thinking. This is what I had originally in mind. Great. And just for my OCD's sake, every once in a while I like to go back and clean up my model just so I can see things more and visualize things in a more productive manner. Oh, this is pretty close. We're going to, just for my sake of, I don't know what drives me to do these things, I was just using trim and extend entities to make this. To kind of pseudo delete a couple of the automatic relations that it had added for us. Oops, don't want collinear. I want perpendicular. Okay, now this just has to be coincident with that. There we go. That's what I was trying to get us to do. I was wondering why this wasn't working. All right, so going back to what I was saying before, we can go two ways. We can either define this is going to be exactly 10.8 inches, and it'll update our model. But we can also have our model be the defining factor. So we can say that we want this bar to be tangent with our bumper. And you can see that it defines everything now. If this condition is true, this tangent, you get this really odd number of 20.29, 12.82. It looks really elegant here in the geometry, but the actual raw numeric values are a little bit odd. Cool. I just wanted to make sure that the stream was still coming. So in this current case, let's say that this is the geometry that we want. We want this to be tangent to our bumper every single time. So that way we can, the hardware, when it's in the lowest possible position, it's going to be at the perfect place to pick up our ball. Now, there's a second thing to consider when we're looking at things like this intake. And it is, I'm just going to make an infinite line that is horizontal, goes there. Now, take a look at this. This line that I just drew represents where this intake roller is going to be as this ball is being rolled into the arm. It means that this intake roller is going to have to compress the ball everything above this line, that is the ball, is going to need to be compressed. It means that it's going to need to squeeze it that much. And we can see here that at the apex of the ball to that line means that it's squeezing the ball 3/4 of an inch, about 0.7 inches. But there's a second thing that's very critical, is that, and that's okay. I think that the roller could compress it 3/4 of an inch. But there's another thing that we really need to consider, and that is currently we're just barely touching the ball up here, and we're just barely touching the ball there. We need to compress the ball in order to have a really good handle on it. So what we're going to do is I'm going to delete this tangent relation that was on the ball before to this intake roller, and the ball is going to stay in the same place, but our arm is actually going to interfere with the ball more. We're going to compress it a lot more. And how I'm going to define this compression is just by taking a line that is, it's just going to be a line that goes here. And this line is going to represent the apex of the amount of compression. So you can see here, currently this line is tangent or coincident with the center of the roller, but when you make it coincident with the center of the ball too, both circles, it gets permanently defined at the apex of compression. This is the maximum amount of compression that we're going to be applying in this particular state. So when we're holding the ball perfectly, also this, sorry, I just want to make sure I get this done, this line is no longer coincident with that circle. It's actually going to be coincident with that line. You can see here that way this line continues. It's going to be coincident with the center. When it was over here, it was no longer defined correctly. When you think about the geometry, it's going to be, this is going to be the tip of the ball. When the ball is compressed this way, this is going to be the tip of the ball now. So you can see how that might line up. And in truth, yeah, we're just going to leave it that way. Now, what's the amount of compression that we want when we're holding onto our ball? Well, that's a good question. These balls are very big. They're 24 inches in diameter. We're going to be holding onto it at 3 points, and the compression is going to be equalized on everything. I don't know, let's give it a shot at 1.5 inches. That's going to be a really good compression. We don't really have to worry about the ball touching here because the ball is actually being compressed. It's not actually interfering. It's just the ball is giving. It's yeah. Now I think I understand now why in the original design they had the pneumatic cylinders on their on these arms. I believe those cylinders were to apply and relieve the compression of their entire system. So when the cylinders were contracted, it would be compressing the ball 1.5 inches or whatever it was. And when you extend the cylinders, it relieves that compression and just applies 0 compression. It's not completely loose and rolling around. It's just not being compressed at all, which then when you fire the puncher, it doesn't have to fight to get the ball out of the compression here. All it has to really do is just roll it on out. It's just pushing the ball out. It doesn't have to fight the compression to get the ball to exit. So they probably have this on a pivoting point here. There was another thing that I noticed here on their design. They did something really smart, which was to add 2 intake rollers. They belted these 2 things together. And what that looks like, I'm trying to see if that belt goes back. Okay, what it looks like is what they did. I'm going to look at the other image. That doesn't really help us too much. Okay. Well, what I think this geometry is doing is when it holds onto the ball, this second roller that's hidden back here is touching the ball also. And I think what that lets them do is I remember seeing them spinning the ball inside their robot. It was just kind of rotating. You could watch the first logo swirl around. And I think what that let them do was help center the ball on the puncher. Who knows why they did that, but I think could have just been a showboating thing too. But they had 2 intake rollers. Currently, we have 1 intake roller. And I think one of the issues that they were coming up with was because of this. Remember that horizontal line that we drew before? This is going to be the max amount of compression that our ball is going to be under. Even though we're compressing it when we're holding it at 1.5 inches, which we've defined with this smart dimension, when it's being rolled into this point, I'll demonstrate this with a more active ball here. This ball is tangent to the ground, and it is the same diameter as this ball. Take a look at as the ball is rolling in. Right at this point, when the center point of the ball and the center point of the roller are underneath each other, you are compressing this ball from the apex of the ball to this bottom, to this imaginary line that I drew. And you can see here, I'm just representing this with the existing ball. It means that we are compressing this ball 2.3 inches in order to get the ball inside of our arm. As you move the ball further along, that compression eases and it releases to the point of being 1.5 inches right there. But you can see here as it comes through, there's no compression. You're starting compression here, and it gets really high, lots of compression, and then it comes back and settles at the 1.5. So that's kind of an issue. We might not be able to compress the ball 2.3 inches. That might be too much to ask for. That might be too much stress on the ball, too much stress on our robot. So I think what Hot did to relieve that issue was they added a second roller. Now, there is something that's bothering me here with the way I've constructed this, is that this roller is on center point. The center point of this roller is on the edge of this. So what I'm going to do is I want to draw a roller that is in the middle of this beam here. I don't want it to be mounted on the edge because that's technically impossible. I want this to be mounted to the center. So we could try to redraw or release the dimensions and relations of this roller and move it, or I'm just going to redraw it in this case. I'm going to re-add all the dimensions because some of the dimensions that we added in getting here are very difficult to unadd. But we're going to see here that this is going to affect the geometry as well. So just give me a second here as I update these. Come on. You know you can do it. Okay, clearly. Oh, I did this silly like. This is tangent, isn't it? Or coincident. That was the issue. It's not that that needed to move up. It was that that needed to move down. I'm going to dimension this temporarily being 1 inch. Invalid geometry. Temporarily, I'm going to delete that number until I get this in the right position. Perfect. Looks like that. And now we need our 1.5 inches of compression, which means that I'm going to re-add this line too, because that line's not actually constrained to this edge of this line here. It's constrained to the edge of the ball. That's what's really important. And it's also coincident with the center point of the roller. There we go. That is what we were looking for. Kind of make sure that this is collinear with that, or that is being coincident with the center point of that ball. It's the same thing. And now we can see here, this is much better. This is the center point of our roller is being mounted in the middle of our beam. Now I'm going to re-add that 1.5 relation that defined the. There we go. Very good. So you can kind of imagine our ball deflating or being compressed to fit that. Okay. Very good. So that's where that's at. We need to make sure that that is coincident here to that edge. And you can see here that's probably what Hot did. Their intake roller protrudes out of their when you touch the first part of their arm, you touch the intake roller first. It is on the the outer edge of their entire arm. So now let's add a second roller. This is going to relieve this issue of this insane compression, I believe, or at least give us some more control over the ball. Now that I'm thinking about it, it might not relieve it, but we're just going to add this to move along. So the important thing is when the ball is held in the arm, this is the position of the ball when it's held in the arm, this roller is going to be tangent to the ball. So you can see here we're really designing the arm around the ball in the position that we're trying to pick it up in. That's what's really important. So now that we have this, well, currently this is having no compression. We want to make sure that this has equal compression with this one here. So what we're going to do is, there's a second way of denoting compression. Instead of having a line, since we're going to be referencing multiple things, I'm going to create a second circle. This circle is representing the compressed radius, or the compressed diameter. So this is going to be tangent to that, just like that. However, let's bring that back down. Before I get too carried away, I need to get rid of that other tangent. Perfect. That's what I was trying to do. And now that 1.5 inch compression between the compressed circle radius and the actual diameter. That's the difference between the two. The compression and the actual is 1.5 inches. So that gives us a really good sense there. This is rough. This secondary roller is going to be located somewhere along this path that it's allowed on. Great. Where do we want to place it? Well, I'm thinking that this 1.5 inch compression is a little much. Let's go back to the 1. That'll help relieve this overarching issue of this compression. This is what we're really trying to relieve. This this total compression. That's the true issue that we're trying to solve. To make this nice and symmetrical, I'm going to make this. Okay, yeah. So to make this nice and symmetrical, I made this this secondary roller tangent to this horizontal line, which was tangent to this one. And the reason for that is when when the ball is, hold on a second, no, that's not exactly right. So a lot of this is just logic. It's a geometry type logic. This is where, if you have a programming brain, that kind of comes in handy here. What's really happening in the greater scheme of things. So I'm going through and I'm designing this myself, and I'm trying to understand it first so I can explain it. So, by adding two rollers, there's something that we can do. We can do one of two things. We can pretend like this is a secondary roller. This is kind of like the position it is in now. We can say, here's the secondary roller. All it's doing is providing a place for the ball to back up into. This is like it's hitting a backboard type thing. Or what you could do is have these two rollers pretend as if they are the same roller, like these are both primary rollers, in which case the ball isn't really being primarily compressed on this roller, it's being compressed between these two. So, and I think that's what we should do. So, in a sense, remember this line that we were drawing before? That was making sure that this line was going to pass through the center of the ball so they have a really good grip. It's and the critical part was that it was lined up with the center of the compression, the middle of whatever's compressing against this compression bar. And if these two are truly going to, two rollers are truly going to share that compression, this line shouldn't be coincident with just one roller. It should be coincident with the average of both rollers, or essentially the midpoint of the line between the two rollers. That's what I've just kind of added here. And you can see how that changed the geometry here. Let me just think about this. We added this as being a horizontal line, didn't we? If I get rid of that horizontal, still isn't defined. It still is fully defined. This shouldn't be fully defined. There's something around here that's making this do something that I wasn't expecting it to. Let me think about this for just a second. I just undid that midpoint relation. That was horizontal before, and this was horizontal before. There we go. That was it, I think. Yep. And this still want to be tangent to each other. Dang it. That wasn't exactly what I was expecting. This guy is horizontal back? Nope. None of these are horizontal. That is not horizontal. So what I think should happen is I should be able to rotate this along. Oh, that's what. This is locked already in place. Yep. So it was doing what I was expecting. It was just that it was smarter than I was. So this imaginary line needs to be coincident or midpoint with that. Right. This is what I was expecting to happen. We should still be able to choose where we have our, you can see all of our relations kind of at work here. Yeah, we can still choose where we want to put our rollers. This is kind of where I was after here. So we can see here that when we get rid of this tangent relation to the vertical edge, we have a lot of freedom for how we're holding the ball. Are we holding the ball very much in the middle? If, for instance, if I just move the pivot point way up here, you can see that we're holding the ball fairly close to the center. But if I drop it down here, we're gripping the ball very close to the edges. And if we're holding the ball that close to the edge, that's kind of a recipe for disaster, or it's probably going to slip and just poke right through the bottom. So in order to define this, let's just make that a driven dimension, and make that maybe 18 inches was a really nice number. So let's set that back to be 18 inches. And again, this is the really raw, straight design talk. This is I don't have very much of a clue of what I'm doing here. I'm designing this for the first time. Okay. I'm going to get rid of that line, because that line, I'm going to re-add that in just a second. This. Okay. There we go. So we can kind of see how some of these relations are happening. If you're following closely, you know exactly what I've got. The important thing again is that I really want to figure out and resolve is making sure that we're not compressing the ball too much when we're intaking it. So for instance, currently, right now, we're compressing the ball an obscene amount in this scenario. If we designed it like this and we built it, we're compressing the ball 6 inches as we're trying to get it rolled into our robot. It's also illegal because our hardware is extending beyond the frame perimeter. So let's start to resolve these issues by moving this back into the perimeter. But we really can't do that currently with all the options that we have selected. I can't really move this back into the frame perimeter. You can see here, it's just not letting me. And that's because we've got one of our relations just isn't letting that happen. You can see here that in order to get this imaginary line to cross the center point, it has to be at this angle. And it's set at that angle because this our bar is coincident or tangent with our bumper, and that has set the slope of this entire bar because the ball is placed at this specific point. You know, if the ball weren't tangent to our bumper and we could pick up the ball farther away, for instance, let me just show you that right now, our slope of our entire arm would change. But as it happens, we need to pick up the ball when it's coincident with the bumper. That's going to be really important because it needs to be as close to the robot as possible. So something's got to give here. Either we something's got to give so that our slope of our arm is a little bit lower. Right now it's too steep because this is truly the issue. If this didn't have to be coincident to the center, if we were to compromise our grip a little bit, we could bring this back, right? We could bring that back. That was a really difficult way of moving it. You know, there are a lot of changes that we can make. We could make this not coincident. We could make this ball not coincident with the bumper too. But I think that the best thing to compromise is going to be the compression here. This doesn't have to be coincident. This line doesn't have to be coincident. That's kind of a best case scenario. But in reality, you could back this up a little bit. It doesn't have to be. As long as you get a really good grip on the ball, this is still a fairly good grip. You're getting the majority of the ball under your own control. So let's set that back constant or tangent with the boundary. So now our first roller is set in place, and now we just need to decide where the second roller is going to be. The second roller might not be too effective until it is a certain amount distance away from the first, maybe 6 inches away. And now that I'm looking at it, 3 inches is quite a big roller. We could probably get this slope closer to the center if we decreased our roller diameter up to 2. That'll still get the job done. So we just kind of added a few more details on getting this thing to work. Now, this beam here, that imaginary beam that's holding on to this front roller, it's no longer looking too happy. How is it going to hold on to this roller and this roller at the same time when it's at this wonky angle? So let's try to get this to match this angle. This angle is set. This is a perfect thing. As you can see here, we're now compressing our ball as it rolls in only 2 inches. I think that's acceptable. We just solved the issue of the compression issue that we've been having. So now when we roll the ball in, it's only being compressed 2 inches. So the next logical thing is to try to get these two rollers that are doing the compression, get them mounted to something rigid, like this beam that we have here already. It's not critical that this beam is perpendicular to this back plate. So let's get rid of that perpendicular. And now you can see here we can change the angle. Doesn't have to be perpendicular anymore. So let's, now that it's not perpendicular, we can set that angle to be parallel with our the slope between the two rollers. So now you can see that there we go, that this beam here is going to be able to hold on to both rollers very well. It makes our arm look a little funky, but it means that it's also functional. We're fitting the geometry to this specific case. Now, there's also this issue here of where is our pivot going to be placed. We can see currently the position of the pivot makes the depth of our entire arm very sensitive, very, very sensitive. And that's because we have this perpendicular relation. If we get rid of that perpendicular, we can see here that as soon as that happens, the location of the pivot point has no effect on where the arm's depth is. So let's keep that perpendicular away from that arm. Let's set that away, because the next thing that we should be worried about now that we have, well, first off, we just reached a checkpoint. We have successful geometry of where our intake rollers are going to be and where our where this bar is going to be here too. I think that's really critical. That's really important. Just for the sake of seeing exactly where we're at, I'm going to draw a couple more of these lines, one to each one of the center of the roller. So the compression that's going through this roller, the force is going directly down here. The compression that's going through this roller is going directly down here, and the average is going right around there. If we really wanted to roll this ball, like I think Hot does, well, like hot does. This roller should be over the center. I wonder if there's another variable that we could tweak to get that to happen. That might just be compression. In any case, I think this is going to work for us. So we'll just leave that the case currently. So we just have a checkpoint. We've got a successful intake mechanism. We're not going to touch that just now. I think that's going to work for us. So I'm just going to go ahead and save my file here because I don't want to lose this progress. I'm going to put this in CAD Lab. Sure, why not? I usually call these things master sketches. I'm calling this project 67. Very good. So there's our progress so far. The next thing is going to be packaging the puncher, right? If we've got a successful intake, we also need to somehow package a really nice puncher. They have a really big square that is the surface of the punching, the interface between the ball and the puncher. And the reason for that, instead of having a single point in the middle, is because you might puncture the ball, or the ball might wander to one side if you hit the ball a little bit north of center, a little bit south of center. Having a lot more surface area spread across the entire surface area of the ball is going to make sure that the trajectory is kind of averaged out, so you can hopefully match the slope of the puncher movement. And the slope of the puncher movement, is dependent on the angle of the entire arm, so that way you can change the trajectory of the ball very, very precisely, very accurately. So the really tricky part is how much stroke do we need here? We can see here that it looks like they have stroke that goes from the back of the ball. This is probably tangent to the ball when it's cocked back and it's ready to roll. It's probably tangent to the ball at that point, centered on the ball and everything. And then when it's released, it is looks like it stops travel here, almost when it's in line with the tip of the on this tip, this imaginary line here. Yeah. So let's define this geometry of what that intake, what that puncher is going to be. So here is, yeah, very good. I'm just going to take a look at more what they've done here. Yeah, okay. I've got the sense of it now. So their puncher is looking like this. They've got, the puncher is going to sit on top of this structural bar, the structural member that they've got going. So that means, and that looks like they've got 1-inch tube for their puncher, so that's also helpful. I would say that let's create a 1-inch profile of their puncher, of their square puncher. So in this case, it looks like that. That's their square puncher. We could make this square tangent to the ball, but as you'd kind of think about it a little bit more in three-dimensional space, even though it looks like it's touching the silhouette, it's not actually touching because the ball is spherical. It's very evenly spaced, not touching this puncher. So it's actually only going to start touching when it's somewhere around here, right? That's when it's around going to be touching evenly across all edges. So we essentially need to Well, they used round tube, and I think that's a very important thing. The round tube minimizes how many, minimizes sharp corners that are going to be contacting the ball. So it looks like this from the side profile view. Here's that. This is going to be tangent with, this bar is going to definitely be tangent with this silhouette of the ball. And this bar is going to be tangent with the silhouette of the ball. And you can see here that this is most certainly not tangent with the silhouette of the ball. But that's okay, since this is an even square. Technically, this is tangent with the sphere. It might not be tangent with the silhouette, but it's tangent with the sphere. And that's what's important. Now we get to define, looks like I need to work on my adding some more relations. So this and that want to be tangent with each other. This and that want to be tangent with each other. Let's make sure I added those down here too. I added one. This is the other one that I need. Okay, that's better. This is what I thought I had. So now the next thing that we get to have, gosh. All right, hold on one second. Let's make those two things equal, and let's make these 1 inch. Oh, make these parallel too. This clearly wasn't tangent. Add that. Great. Now we can add this distance. That distance, let's say that's just 1 inch. I used 1 inch tube, 1 inch diameter tube, rolled it all up. What I was trying to get to before was now we get to decide the size of the square. This length that we're looking at currently is going to be matched depth-wise, so it's going to be a square. It's going to be centered on the puncher. The puncher is going to be centered on it. Before we set that width, well, I guess we could set it. No, it doesn't hurt. Let's say that that width is going to be 8 inches. That looks about good. That's a good size. A really important aspect of if this is the shortest distance between the pivot point and the center of the ball, this arm length here, we want to make sure that the stroke of this is going to be, I guess it doesn't, technically it doesn't have to, but for simplicity's sake, the stroke of this piston kind of wants to be parallel with the length of the arm, right? Whoops, my bad. I thought I would have different selections. Here we go. The stroke of this piston kind of wants to be parallel with the arm, as if it were collinear with that. Then this line is from the center point of the pivot point to the ball. So I guess another way of saying that is the stroke definitely must be coincident with the center point of the ball. That way we're hitting the ball at its center, hitting the middle of the ball square on. That's exactly what we want. We're not hitting it too high, we're not hitting it too low, we're always hitting it centered. That's important. The next thing is where is this going to be positioned? We could have it up here, right? That could be okay. That only means when we shoot, we need to lift the arm, a little bit, lift the arm a little bit. I guess it could be simpler and easier for the operator to judge the angle of release if this puncher were collinear with the arm length, right? If it matched the arm length, if it were at this location here, that would make the operator's job easier. In the end of the day, we're trying to make a tool for the operator to get to get the tasks on the field done. It's all about the operator. The robot's just a tool. This will make the job easier for the operator. So there's that. That's going to be a position. This is the cocked back position of the puncher. That way, the ball, when it's sucked in, is going to be, it's going to skim across. It's going to be touching this at all times. It's going to be touching the puncher at all times, which is really good. That means the ball is going to accelerate with the puncher as it's released, which means that you're not actually punching it. You're more kind of pushing it. You're starting it from zero, and you're not hitting it in the face. You're kind of pushing it across, which is important too. That means it minimizes shock in the ball, which means that it's not going to go off and travel in unprecedented directions. It'll be very predictable when you're pushing it, not punching it. So there's that. That's really nice. That's a really good position for where the puncher is going to start. Now we can also define where this, I'm going to make this back brace parallel with the puncher, which means consequently that this and that are no longer perpendicular, so I got rid of that. We could keep that perpendicular relation if we deleted this tangent relation down here, but then it would be, this arm would be compressing into the bumper, and that just gets messy. So I got rid of that perpendicular. These two things are parallel now, the puncher and the back wall. That way it'll absorb all the force as evenly as possible. Makes geometry cleaner. And you can, now what we're going to do is, I think what would be smart to do is set, oh goodness, stop it. There we go. That's what I was trying to get out. I wanted that out of the way. Is set the distance between the back of this puncher and the this edge of the structural edge of the material of the actual arm, the rigid structure, body structure. So let's just make that 1/2 inch. Give us a little bit of clearance. That way, if something ever goes wrong, or actually, let's make that a 1 inch because we're going to need to put a limit switch back there, right? That way we know when the thing is fully drawn back. So that'll be really important. Having a limit switch. That 1 inch will give us enough space, I'm sure, for a limit switch. But look at this. Look at how nicely our geometry is becoming defined. You can see here that our pivot point is set to be on a slope. And that slope is set because we wanted this this arm to be the same, to match the slope of the puncher. And the puncher has a set slope, and everything is, or is it? You know what? Hold on a second. That doesn't seem quite right. There's something that I'm missing. There's that. There's this. That's collinear with that. Midpoint with that. That's fine. Since we broke that perpendicular relation, I would have thought that this would still be able to, that's what it was. I think, oh, I didn't. Wow, okay, just joking. I thought I made that parallel with this, but no, that's at an angle. So that means that there is a relation somewhere in here that is, what should happen is this shouldn't be fully defined still. I should still be able to move, change the slope of this line somehow. So what is it? that is defining it. That's parallel, that's fine. What happens if I delete this? This is what I was expecting to happen. I was expecting that to be able to happen. So I just got rid of that line. There's some constraint on that line that I didn't understand. So now when I go and I re-add that line, like this, and I make that, oh, I know what constraint that was on the line. If I go back and I pretend like it was on there again, I bet you it's this midpoint. That's it. That's what I was expecting to happen. I put a midpoint relation on the tip of this line and on that that back wall, that back brace. That was what was going wrong with it. This is what I was expecting. So now we can still move this pivot point freely in space. I think that'll be of value later on. Great. So there's that. The next thing that I think we should define is let's draw a second position. This is the puncher when it's cocked back. Now we should define the puncher when it is fully released, in essence, its finished stroke. So that means that we're going to draw a second case. I don't like looking at these. I'm going to get rid of them. They were helpful at the time, but they're not actually used for defining the geometry, so we can get rid of them. I am making these coincident with the circles because we are reconstructing a second one of these puncher pieces. You know, I could have copied and pasted the geometry. I realize that now. Haven't done this in a while. I guess I really could have. So lessons learned, but I'm almost done here. Almost done adding all these, making these things tangent with each other. Next thing is to be making these equal to the previous one and make this line length equal as well. We want to make sure that this and that are parallel. And just for good measure too, let's make the, there we go. This line here that I've drawn, you might not have this in yours, but I drew this line to symbolize the stroke length. This is the length of, you see here, it starts here on the back panel here, and it ends on the back panel of this one. So this kind of represents when it starts, it's back here, and then when it finishes, it might be somewhere out here. And this line length represents the difference in movement that it's had. So you can say here that, let's say the stroke, the entire stroke of this thing, we were going to move the ball 10 inches. I don't know how much is needed. This would probably be a number that we would get from prototyping, as well as the compression number. I don't know. I'm just pulling those out of my head. But let's say that that it takes 10 inches to fire the ball repeatedly. Now you can see here that this is rigidly attached to the rest of the arm. And it's all very nice. When you move the pivot point around, you can see that you're really changing the entire geometry of the arm. Now, a really important thing, I think, is, well, let's see here. I have to think about this. Okay, yep. I think an important thing is going to be when we're firing this ball, what's going to be critical is that it is being rolled across on a floor. Currently, it's when the ball fires. Let me just come back over here. Cool. When the ball fires, it is being rolled across on this on these two rails. This makes perfect sense. So there are two positions of this rail, these compression rails. It's actually doing more than one thing. It's being used as compression bars, and it's being used as rails for firing. On this puncher, it needs something to help guide the ball out of the entire shooter. So when this pneumatic cylinder fires, this will rotate down, and it will rotate down until it is parallel with this puncher. You can actually even see currently with the cylinders it's in the compressive state, and that it is not parallel at all to the puncher stroke. But you can imagine when this bar does extend, it will be parallel with the puncher stroke. I bet you it'll be parallel with the puncher stroke. In that way, the ball will have something to roll across without any interferences as it's exiting the ball, as it's exiting the shooter. So currently, it would be very easy to say that, well, this is going to be parallel to the puncher stroke, right? Puncher stroke is going to be parallel with that, and that's what it's going to look like. Seems simple. However, we have to remember that there are two positions. This has two positions. It's going to be in the down shooter position, or it's going to be up in the compressive position. This currently is representing the compressive position. There's going to be a separate position that represents the shooter. So let us define this more. It's going to be a little bit tricky to define it in the current geometry, so bear with me while I modify this geometry to make it easier to visualize and easier to engineer. So I'm going to add a line that goes here. Ooh. And come on, buddy. I'm going to temporarily fix this so I can move that line further out. Oh, no? Fixing it over-defined it because that line was semi-defined. If I fix this, it should be fine, though. Where's fix? There. There we go. Now, we can make that and that coincident. So what I'm doing is I'm making a solid beam, pretending like this back plate is one beam, and this is a completely separate entity, which in true fact it is. It's going to be a completely separate entity. The one that pivots on this beam, it's going to be centered on that beam like that. And I'm going to make that construction geometry. Oops, not that. This construction geometry. And we will extend, well, we'll trim this entity here. Oops, well, we'll extend that entity up there, so that way it touches there. And then we're going to trim this entity there. And then, actually, you know what? Let's just make this nice. There. This will be good for demonstration purposes. Perfect. So what I've done is I have reconstructed this joint that was back here, right? I took Actually, there's probably still some arbitrariness happening here. Let me take care of that. If I take this and make those two things concentric to each other, make that and that tangent to each other. Didn't have it in the right position. Couldn't make it tangent in that way. I was trying to do something impossible. Oh, come on, you know you can do it. Maybe it's just having a hard time working with that concentric. But if I make that tangent, start with a fresh one. Might have added a geometry that I didn't want. Ah, yes. This radius is 1. This radius is 1. So it seems that they could be tangent or concentric with each other. And in fact, they could be. So it makes me a little bit sad that SolidWorks is throwing a little bit of a fit. Can't figure out how to make them tangent. But surely they can be tangent, just like that. But what I was aiming to do was get rid of some of this extra geometry. Make this joint a little bit simpler for us to visualize. And maybe even put this on the robot. But you can see here now that there are, this is what I was trying to get at, there are 2 sections of our robot. There's this bottom one, and this is going to be able to rotate up and down. And then there's this top one. This is stationary. And we can make these 2 things, theoretically, together. Aha, that's why I was being so annoying. These things need to be together. And now, I bet you we can make these constant or concentric. There it is. That's what I was trying to do. So, just going back a step. So we've got 2 parts. We've got this one down here. This is going to be a compression bar. And then we've got this one up here, and this is going to be the intake bar and the back panel and the back bar. And these are going to be 2 completely separate parts, but they are going to be joined at the hip right there. That's going to be a pivot point for this bar to angle up and down. It's going to have 2 positions. And so what we're going to do is we're going to define, well, firstly we're going to save, because saving is always a really good plan, especially after you do a really complicated thing. We're going to define a second one of these bars. So I'm going to take one, copy it, and then paste it somewhere else. And very good. Hopefully it kept the relations. and I think it did. But we do have to keep, we have to make these two things equal to each other. Since it's the same piece of hardware, just in two different states, they aren't going to change dimensions. So what we really do need to do is make sure that they're going to be the same no matter what. Looks like I had them parallel with something or perpendicular with something else. It was not my intention. I should be able to take this one and rotate it differently. Yeah, see, that's the important part. All right, there we go. And let's, for instance, right now, let's set an arbitrary length to one of these as being 18 inches. Now this is going to be concentric with that because it's going to be in the same language, like that. And this has two states, right? This is the intake state, and then when this is parallel with the stroke, that is going to be the firing state. However, we have to make sure when we do that, the ball is going to move. I realize. So the ball is going to have two different things. So let's think about this. Okay, yep. There's a problem with this one, this generation, because currently when you're in the firing state, it lifts the ball up, which means this is no longer centered, because this ball is actually shifted up and this shooter hasn't shifted. And it also means that that the ball is being compressed against this bar more, which is not good, which means that we have to go back into the design a little bit, and we have to change a few things around. What we have to change is we have to change the positions of these. Currently, we do want to have two states, two firing states, a firing state and an intake state. However, the firing state, in this case, moves above the intake state when it really should drop below the intake state. So, the way we're going to achieve that is, well, we may have to compromise on a few things. So theoretically, you know, this could have worked down here. This achieves what we want. The intake state is up here, where it's tangent here, and it picks up the ball, and it gets stored back here, and then it's perfect. And then when we're ready to fire, this blue, the top blue one drops to the bottom blue one, and then it can, it's then parallel with this, the stroke width, and then it can fire it out. However, that doesn't work too well with our geometry because it is interfering with the bumper. So what can we do to make that better? Well, we know that it really has to be tangent to our bumper. That's as low as it really can go. Whoops. Gotta make sure that's the right kind of tangent. It's gotta be above. There we go. So there's that. Let's take a look at their design again, because I'm getting a little bit stuck here. How they achieved this. Okay, here's an idea. What happens when we change this number? What if we change this to 9 or something small? We get invalid geometry. So what I'm going to do is I'm going to set this to driven, which means that I can change that number with other things. And I want to see what happens when I drag this down lower. Oh, somehow we lost the tangent relation, so I want to put that back in. There we go. I want to see what happens when that does this. There we go. That's what I was really interested in seeing. So what it looks like is if we wanted to keep this tangent in the lower position, and then in the firing position, it's okay in the firing position if this runs into the bumper, because it's actually never going to be in this position when we're intaking. The arm is going to move up, then move into the firing position, which makes sense, right? So what to do here. So we want to make this parallel with that. Now, theoretically, that should have aligned everything. Interesting. So it looks like we still have some freedom here. We have some freedom to make this ball wouldn't it be cool if we improved upon the design? Oh, no, that doesn't work. I was going to say, wouldn't it be cool if we improved upon the design and we made both of the positions the same position so it didn't have to actuate? That way the intake position was the firing position. And that would be cool, except that it still has compression. So we need to relieve the compression somehow. So here's the intake, and there's the compression. And the compression is a really good point because we need to make sure that the difference between the two. So here's the ball. This is this. In this case, the compression. The distance between these two should be the same distance between those two to minimize compression. So the distance, the angle distance that this moves needs to have the effect of relieving 1.5 inches of compression or whatever we put on compression, and then some. So by drawing another circle and making it tangent to the fire position, we can make the comparison between these two, that the difference between those two is going to be the difference in relieved pressures or compression. So currently our compression is at 1 inch. We can actually just set an equation to say that this equals that 1 inch of compression, no matter what we've got, plus a little bit, plus 1/2 inch. That way there's always going to be a 1/2 inch of a gap. Great. Look at that. We just fully defined that. I think that's going to be functional. So there's going to be this 2 states. This is what's really kind of important. There's 2 states here. There's the intake state, which is here. I'm going to highlight this in 1 because it's getting difficult to see it. So there's the intake state in green. And then we're going to pretend that we move the arm up in a new position. Then we're going to relieve the pressure by moving it down here to the firing position, which relieves the pressure. And when the pressure is relieved, and then some with a little bit of an extra 1/2 inch or so, 1.5 inches, it will be parallel with the length of the stroke. Because we set, you can see we've got a parallel relation between the stroke and the bottom here. So that way they'll always be parallel. And even still, in the pickup position, it's tangent with the bar here, with the bumper. So we ended up fixing everything that we wanted just by tweaking some variables. We got all the functionality that we wanted from this thing. While we were defining this, because we had to define so many small variables to make everything work, wouldn't you notice just joking. That was a lie. I was going to say I was getting a little bit confused of why that was. I had fixed this before. So you can see here that we still get to choose where our pivot point gets to be. The shooter is functional no matter where it goes. It will intake and it will shoot just fine because of the smart constraints that we've added. You can see even when it's way up there, it'll pick the ball up here and it'll drop the ball off there, and it'll work perfectly. So I wonder if there is, so now we get to, you can see here that as we move it, we get to, we're changing the left and right positions of our bars here. So you can see here, as we move one of the bars in, it changes the position of our shooter. So let's set this back at 18 inches. We had undone that so we could see a few things. So when we set that at 18 inches, it defines one dimension of our robot. So our pivot point is going to be somewhere along this line, and it'll be good. So where is the other thing? I mean, hold on a second. Just look at that. We got a checkpoint down here. The only thing that's still blue are the ends of these lines, and you know, we'll just we'll just pretend like that doesn't exist. Actually, you know what? Let's make this a 3-inch diameter roller, and you'll notice that everything updates and it'll still work well. And now, since that's a 3-inch diameter roller, the actual aluminum structure doesn't get in the way. It'll always contact the roller first, rather than contacting the structure first. And we'll just make this really nice and pretty by, whoops, I didn't need to do that, by rounding off this end. We'll make that concentric with the roller so it's super nice. And then make that end cap tangent. Perfect. So look at that. Look at that complexity. But when you look at it and you're building it, you don't see all this extra crazy construction geometry. It'll just look super elegant. It'll look like, of course, it was designed that way. Why would it be designed any other way? You know? But it takes a lot of thought and a lot of effort to get it to work. Very good. So here's that. There's that. That's all very nice. Now, how tall is this pivot point here? That's what I'm curious. If it's up here, I want to get some numbers on the range of where this pivot point can be. I'm just going to define it here, and I'm going to define it here. Very good, and I'm going to set this to being driven. So it can be, you know, 9 inches from the side and 38 inches from the top, from the bottom, or it can be 31 inches and 18 inches. You know, we could center this on the middle of our robot if we wanted to. We could pop it right down there in the middle, and that way it would be almost symmetrical. You know, we could. You know, it would just our pivot point would be in the symmetrical center of our robot, which could be cool. But what does that really get us? It might not get us much. What might be beneficial? Well, let's take a look at what Hot did. Let me zoom out. here we go. They mounted their pivot point way up here. This is where their pivot point is. Looks like that sprocket, that's the actual pivot point. And you can see it's very close to the front of their shooter. Surprisingly close, actually. Even though it would look like it might be back here, it's actually up here. This is just the structural beam. So they definitely mounted theirs. They might have mounted theirs in the middle. And you know, that would make sense. Mounting that in the middle would make sense because then as your clearance for the arm that you need, the back of the arm is maximized. So for instance, let's say that you had, in order to make this entire thing work, to package your shooter, you needed to have a chunk of a really big chunk of mechanics. This box that I've just drawn here, for instance. My goodness, the computer is being super slow. Excuse my computer. You needed to have a box of mechanics that was maybe 18 inches long, and was, it was parallel with this thing. And so it took lots of extra space in order to actually rotate your arm around. But to rotate your arm, to get it to the other side, it's kind of dangerous, right? You don't want to protrude your frame out of your frame perimeter. Although, now that I'm thinking about it, well, I mean, what I was trying to get across was that if you center your pivot point here, you don't have to worry about, all the mechanics that are centered on your pivot point are just kind of centrally located there. But a really good point, actually, that's a different point that I wasn't really making before, is center of gravity. The lower you get your the weight of your mechanics to the ground, the lower your center of gravity is, or the center of mass. Where is all the weight of your robot? So if we decided to mount our pivot point way up here, which totally could, that's completely legit. We could do that, but that could be, that would, if a lot of mechanics had to be up there, that could be very dangerous for making our robot top heavy. We could also mount it lower to the ground down here, which would be beneficial for center of gravity. However, when we lift up our arm and we try to fire, it might not work as well because our arm wouldn't gain much height, right? If our pivot point was here, our arm would rotate up and it would just be up there. But if we look at how long our arm is when our pivot point's back there, and how short our arm is when our pivot point is here. So there are kind of trade-offs. As you go over here, your arm gets shorter, but your center of gravity gets lower. As you get back here, your center of gravity goes up, which isn't as good, but your arm gets longer, which could be good. So you kind of have to find some sort of balance. And finding that balance of where to place the pivot point can be achieved by drawing another model of your arm, except this is going to be in the shooter position. So at what angle are you going to be shooting your robot? Let's take a look at the hotbot here for a second. I don't remember if the Hotbot was designed to shoot from both sides or not. Let's see if we can find some sort of video on that. Here we go. So this is their robot. This is clearly one of their matches. And it looks like they're right there. There they are. So they're intaking like that. Okay. So that was very clever. So they pick up on one side. Let's go back to the Auton because they showed that very well. So they shoot with the prongs in the air, the upper side. They fire it out and it goes in. And they pick up with the prongs down, just like we've been defining. So this, the actual reason behind using the two rollers, I think, was more to provide a guide surface. So I guess in truth, it's not as critical that this is parallel with the puncher, but I think it would be a good thing. That way that you don't have to, you really don't have to fight it. But that definitely does pose more of a design challenge here on our, oh, hey, look at that, infinite loop. Poses more of a design challenge for our specific use case. You can see here that they did figure out a way to get their intake rollers to be parallel. Both intake rollers, the imaginary line between the intake rollers, always parallel with their shooter. Now let's take a look again. I think I know how they accomplished that. Let's look at how they pick up balls. So they're just going to fire this one, but let's watch how they pick up the next one. Okay. Now I'm noticing something very interesting about their geometry. When you look at their bars, their compression angle, it actually fits entirely within the drivetrain. It's not cantilevered outside the drivetrain like I had assumed before. From the pictures that I had, I didn't really have any good way of knowing that. I guess I can see it now that I've seen it in the video. But this geometry here that we've defined is partially true. It's partially true, but they've actually been very smart, and they didn't cantilever their entire robot arm outside the robot. They have this entire length here is pushed back into the robot. So now we've got the challenge of, let's go ahead and save our work here because we don't lose it. Now we've got the challenge of fitting this inside the robot. So what is constraining it? What's constraining this what's constraining this into place? It's more this how can we move this entire 18-inch long piece back? and we'd have to move this point back. What's holding this point back? It's going to be this, the puncher. How can we move the puncher back? Because it's more of this wall here, right? It's this wall that's really keeping us in. I bet if we take this 1 inch off, you can see here we're getting really close. All right, that's kind of what we want in the end. We want this to be self-contained inside the robot frame perimeter, just like that. But how do we bring the robot puncher and everything back with it? And I think the question more is, where is the ball when the puncher is contacting it? And where is the ball when it's being initially picked up by the intake arms? And those are two different things. I think those are two different positions. So I believe if we take the concentric or tangents off of that, we can move this entire puncher system back. Whoops, I exited the sketch. That's fine. We're going to re-add this 1 inch dimension I deleted just for demonstration purposes. And we're going to add another ball. This ball is the same diameter as the other ball. And it's going to be tangent. Whoa, that was unexpected. No solution found. It's complaining about this 2 inch thing. I'm going to rebuild because there's nothing should be going wrong. But clearly it's not happy. So let me get rid of that equals relation that I just added. Maybe it's freaking out. Oh wow, look at that. That was exciting. Okay. You know, another thing that could help is right. Okay. So looking at this, those two rollers are very, very far apart from each other. And in fact, it looks like this roller is directly across the tip of that of this end. So what we really could do is delete the 6 inch arbitrary number, and it's no longer going to be tangent to this ball here. I think the reason for the double rollers was to have one manage intake and pass it off to the other roller that would hold it further inside the robot. That's the reason for the double rollers. So if we take a this intake, tip of the intake compression bar, and match it with the secondary roller, we get this spacing here. So look at that. Now, as the ball rolls from, I'm going to make this parallel with the shooter. That way, as it leaves, it's exiting just, you know, a hollow tube, and it's not tapered at all. But now, as the ball enters, it's being compressed between the floor and the intake roller. Then it's it's squeezed between the intake roller and the bumper. I'm going to look again at the YouTube video. Take a look if their arm moves up a little bit, as if the compression was significantly increasing as they are picking up a ball. You know, it didn't look like it was moving up that much. Yep, looks fairly yeah. Good. All right. So there's a way to do it. Great. So what we've learned here is that there's minimal movement compression difference as well. Let me just illustrate this with another ball. So here's another ball. In truth, it's actually not always going to be tangent to the ground in this example. So it's going to be moving along, and it's going to make first contact with the intake. And the intake is going to really compress it, and then it's going to hit the bumper. And when it hits the bumper, then it's going to roll up into the robot. You can see how much it's compressing. It's compressing almost 3 inches before it gets stored completely inside the robot. And it's quite obvious that there's way too much compression inside the robot cavity currently. So let's see if we can fix one thing at a time. We're going to use this ball here that I've just drawn for illustration purposes as an actual defining element of this robot. So a really important part is going to be this ball is going to be the it's going to be representing the position of the ball when it gets fully held inside the shooter. So it's going to be tangent to the back wall of the shooter, so it's always touching, and it's going to be tangent to the bottom, or this the rail that we've been drawing this entire time. However, the rail is no longer going to be tangent to it's no longer critical that the rail is tangent to the bumper, right? Because it's not going to be resting on it. So all that really matters is that the interior this riding rail edge of the ball is tangent. There we go, just like that. It moved on us, that's fine. What happened here? So it did move on us, but I guess it's not too fine. Let me, because it looks like the original ball, or the new ball kind of moved where the original ball was. Let me Control Z that. Ah, there's a tangent. That's not supposed to be there. It was an old tangent. There we go, much better. Now, this entire shooter module is moving as one. But you can see the intake module part of the shooter, you know, the intake piece that's over here, it stays put because that's where it's defined to live. That's where it's supposed to be. Fantastic. Now there's another section here. As this entire shooter rotates, it needs to make sure that it's within the frame. Particularly this intake bar down here. Let's say even when it's in its lowest position, like let's say we had a pneumatic firing issue, we want to make sure that that is never going to be interfering with the frame. So I'm just drawing this circle, a really large circle, starting at the pivot point, and it ends at the farthest position of this this flap. It should never be in this position when it fires, so I might as well use the upper position, but just in case, I want to use the lower one. And then we just want to make sure that, well, I'm going to fix this point here so that'll make it easier to demonstrate. This circle represents the point at every single point as this arm rotates. So as this piece of the arm rotates, it's going to be traveling along this arc. We want to make sure that that arc never hits this corner of the frame, or else it's not going to actually nest inside of our frame very well. So what we're going to do is we're going to dimension the kind of the intersection of the frame and that point. We're just going to set that back maybe 2 inches to give us a little extra room. So now it'll always be 2 inches away from the frame, like that. And we're not done yet. We have a fixed point here. We got to get rid of that. So that gets us one step closer, right? So now our shooter and puncher is located in space relative to the frame, so it can't move backwards into the robot anymore. The next thing to do is, let's see here. What do we want to do next? Just going to make that construction because that's not the actual ball, it's just a thing. This is a really good checkpoint. This kind of gets us really close to where we want to go. All right, so I think the next thing that we want to be doing is making sure that the compression, as the ball moves across the entire way, is not too crazy, not too crazy of a compression. So, for instance, as we are, let me select this chain here and make it construction so it's not as visually dominant. So we've got the ball as it starts on there at the bottom. It starts tangent to the ground. It's just sitting there. And it's going to run into the intake wheels, which is going to compress it. How much is our compression? 1 inch. So it's compressed 1 inch at this point. And then it's brought up into the robot across the, over the bumper. It's brought over the bumper. And it looks like that compression is going to be around 3 inches. However, that's not too bad because the arm can move up a couple of inches to relieve some of the pressure. Then it's brought into being compressed against the these bars, these compression bars that I've been calling them. We want to make sure that we have a solid grip on the ball, right? And the tip of this compression bar, from the tip of the compression bar to the or I should say, not the tip of the bar. I want to say the intersection of the compression bar and where it's actually touching the ball, and the same point for the roller, which is essentially the center point of the roller. I actually drew the line correctly. That line, we want to make sure that it's over the center point of the ball. That way we're really holding onto it tight and it's not going to slip out. And we can go ahead and just define that length here. Maybe we just want to have a 1 inch. 1 inch over. We can also define that's going to take a second to think. I think it would also be wise to ensure. All right, well, currently, lots of thoughts going through. There's lots to do in this model currently. We need to make sure, first off, I'm just going to list the things that are going through my brain. We need to make sure that the ball can be successfully passed to this secondary roller, right? We need to make sure that this roller can get it touching this secondary roller. That way they're always, that way the ball is always in control of the robot. We also need to make sure that the we also want to make sure that the this roller there's a lot to think about in this model. My brain just kind of stopped working there because there's lots of concerns. But you can see here, this is kind of a position where the ball would be transitioning between the two rollers. And it looks like it could be a fairly successful transition. Looks like the secondary roller might be able to bite into it just enough. But to make that a little bit less nerve-wracking, let's see, that is the pivot point that's moving around. That is the pivot point that's moving around. So I'm going to take that pivot point of ours and I'm going to fix it somewhere because there are too many undefined variables going on. There we go. We also want to make sure, let's take a look at this. Relation that we added was deleted. Oh no, it wasn't. I was looking at the wrong circle. That's the ball. Okay, so that's fine. I'm just looking at the movement here, looking at how it can be defined. What would be the optimal place for it? And the optimal place, of course, is that when it's down here, if we place the ball down there, we could do that. However, what I notice is that the ball is interfering with the drivetrain and the bumper. So we want to make sure that the ball is always on top of the drivetrain and the bumper. So it's got to be at least up here, at least, maybe a ½ inch above the drivetrain at all times. So I'm just going to add I guess not at all times, at the specified time of holding the ball in the shooter. There we go. That's a beautiful thing. That's a nice sight. Okay. Next thing, intersection there. Is that parallel with anything? That's got a distance. Now, shouldn't this I should have the ability to take this intake roller and move it to the right or left. And I'm trying to figure out why this is fully defined, and it shouldn't be yet. So if I look at the constraints I've got here, I've got that intersection and it's merged here with that circle. That circle is only equal, and it's got a smart dimension on it. Or it's got this line. If I delete that line, now it can move up and down, but that's not my concern. I'm trying to get it to move along the edge here. So it means that this line here is defining it. Oh, and of course it's this. That smart dimension. There we go. That's what it was. So we can define where where we're trying to define now where this line is going to be, this force line. And it can go, since this is also needs to be promptly ejected from our well, hold on a second. Let's think about this. We really need to make sure that the more important detail is that the ball can be transferred from one roller over around the bumper to the next roller. Get a decent grip in that. Get a decent grip, and then be stored inside the robot. And so somewhere along, this section over here, I think is promising. So if I draw a compression ring or a compression diameter here, and I specify the compression between this and that, and I specify the compression that it's going to be compressed between this ball here is symbolizing the moment that it's touching both rollers at the same time. So it's being compressed by both of these rollers at the same time. So you can see here that I can change where the position of the ball is when it's being compressed by these rollers. So I also want to make sure that this roller here that I'm moving functions to hold as a stop, to make sure that this ball, that's the ball that's already contained inside the robot, is going to be compressed well. Right? It needs that one needs to be compressed as well to be held in place. So I'm going to add a compression to this one as well. So if I make this tangent with that will kind of pseudo. So what it'll look like is there's going to be less compression between these two. Because this is so high, if we had decreased the compression, it would kind of come back down. So it's gonna need to. The compression is very soft when it's being transferred. So what we should try to do is move the shooter forward a little bit. So what if this were 1.5 inches from the frame? That was anticlimactic. Okay, there we go. So it should be I want to understand this a little bit more. Yep, so I did have that constraint set up right. I'm just going to re-add it, because I don't know why I didn't apply it the first time. If it were 1.5. Whoa. We lock this in place. Make that 1.5. Should move the shooter. All it does, actually, though, is it just shortens the length of this arm, which I understand now. So it was doing its job before. I just didn't understand it. So all it was doing is, instead of moving the entire shooter, it was just changing the length of this arm, which is still valuable, and we want to make sure that the arm doesn't run into the drivetrain. So we're just going to leave that there. And we can probably just leave that back at 2. You can see there how the arm just got shorter. So the next important thing is, looks like it's going to be figuring out an optimal space looks like the angle is what's really defining how far forward this is, how far forward the shooter gets. So if we set it at an intense angle like this, we can see that it's going to roll right in, and it'll have very nice compression going across the entire way until it gets inside. If we look at the robot again, let's look at the angle that it picks up the ball at. So that's a pretty steep down angle. Right there, right? And it matches the angle of that brace. When they fire, they match the angle of the brace. So that brace is this brace here. So they chose to make those things parallel to each other. And I'm an advocate for centering things. So I have centered the pivot point here on the robot. And with those two constraints, that is a fully functional intake mechanism. It has really nice compression all the way across, has a first intake roller, a second intake roller, and a successful pass between the two. It's got really nice compression on this compression bar when it is in the upper position. It's got exactly whatever the compression was designed as, 1-inch compression. And then it's got, when the compression bar releases, it has 1.5 inches. It's got 1/2 inch of just looseness. And so it relieves 1.5 inch for the 1-inch compression. And then when this entire thing lifts up and it decides to aim into the shooting position, the this bar here, the compression bar, will get out of the way, and this also acts. This top bar is parallel with the shooter stroke as well. We made that parallel with the shooter stroke, so all these things will be parallel, which will make it a very linear exit. It hopefully won't hit too many things. The ball won't hit too many things on its way out. You can see here that they simplified some of the geometry, but instead of making it a harsh square up here, that harsh square corner really didn't do much to help I guess, the weight of the machine, as well as the just the function. That harsh square corner didn't add any function to it. So they cut the corner away. They still kept this really big, beefy brace. And they routed everything here. You can see that. Yep. Got a pivot point for their bar down there. Very nice. Oh, this is a very cool design. So the next thing that they have to concern themselves with is the as much stroke as you want to get out, push the ball, you have to have that much storage space for the piston behind it. So that's a question for us. If we have so much stroke here, do we have enough to balance it on the other side? And I think it's just by a visual guesstimate, we definitely do. So it won't be running into the floor or the bottom at any time. So this is an observer's take on how they designed the robot. There are clearly many differences between the two. If we wanted to, we could add more detail to this drawing, but at this point, this drawing is ready to be made into an assembly, get the parts out the door, and get everything rolling. Yeah, I think this is a really good sketch. Gets us to where we want to go. We can always go back in and change the variables, retweak everything. If we've done our jobs right, and if we've got all of our relations very smartly and added, or very familiar with how we've built this part, we will be able to fairly quickly make modifications to make the entire robot easier. For instance, I noticed in their robot design, if I zoom in a little bit farther, the pivot point for this arm here is up a little bit. It's not actually here. It's not actually at the center point of our, I believe it's not. Yeah, we can kind of see it here in this one better. It looks like the pivot point is actually up here. It looks like it's an inch or two above the actual bar. Currently, our pivot point is at the bar, so we could go back in and we could drop the bar an inch underneath the pivot point and really make that better, make it match what they've got, or the entire intention isn't to match what Hot has done. The entire intention is to make it buildable. We might be able to add a shaft right at the center of that bar, but it could be easier to add a flange, an inch-long flange, just for manufacturability. It can get the same job done, right? As long as but it might be easier to manufacture and easier to assemble, easier for maintenance as well. So even though the geometry is a little bit more complex, you save a lot of, it's much simpler later on. So this is a very powerful sketch. Now we have dimensions for a lot of these things. Like this length of the arm up here is about 26 inches. The entire width of the thing, height of the shooter, is just under 24. It's giving us a lot of really good numbers that we can take further. We can add the 4-bar flippers. We can, as soon as we get this into 3D, we can add the 4-bar flippers. And we can really make this entire robot 3D and reference this one sketch. Infinite loop.